So this lecture will focus on one specific kind of multiprocessors called coherent memory multiprocessors or coherent shared memory multiprocessors. So far in this course, we have covered quite a lot of the goals we set up for ourselves. So we already done the virtual memory organization, and we looked at memory level parallelism, and we also looked at some of the benefits you can get from avoiding one of the limitations of multiprocessors, which is the bandwidth limitation. Today, we're going to focus more on understanding how and why multiprocessors are built. So cache coherence, memory models, and synchronizations will be covered in this set of lectures. We will also heavily explore the kind of parallelism known as thread-level parallelism. Back when I first got interested in multiprocessors myself, they were only used by real rocket scientists, die-hard people who really wanted to solve big numerical problems. The picture here is of a machine called the Thinking Machines, made by the company was called Thinking Machines. This computer is called Connection Machine. More specifically, this is Connection Machine 5. And back in this era, the multiprocessors were supposed to be weird and nifty. Every time you come out with a new multiprocessor, it had to be different from the previous one. It had to have more blinking lights. It had to require new nifty languages in order to solve the problems, and so on. What happened later on in the middle of the 90s was that suddenly commercial interests started to discover multiprocessors. In the beginning of the 90s, if you divide the server market here in two dimensions, first you divide it by how much they cost, so that sort of corresponds to size, and then you divide that between high performance computing, so that's technical computing, this the die-hard scientist, and commercial computing. Turned out that the commercial computing had a big bulk of the market. Still, these nifty machines that we saw in the previous picture, they were only going for high performance computing, and actually they were only going for a small portion of that market, which was the high-end market, machines that costed more than $1 million to buy. So what happened in the beginning of the 90s and what peaked at 1995 was that suddenly Unix machines supporting multiprocessors or shared memory servers started to dominate the market. So they ate the whole multiprocessor market, and all those nifty machines, like the Thinking Machines company, they all went out of business. Now we have another kind of multiprocessors, the multicores, where you have several CPUs or cores on a chip, often connected by some kind of cache hierarchy up to third level caches, and then with some memory interface that we all carry in our laptops. So multiprocessing has really become popular these days. As you will see later on in this course, there are many types of multiprocessors. So you can divide them according to some kind of classification into SIMD and MIMD, and then you can divide MIMD processors into finer categories. We're going to discuss this later. I just want to highlight right now that what we talk about in this course and highlighting much of it still will only cover a small portion of this market. More specifically, this next couple of lectures will look at small-scale shared memory multiprocessors, coherent shared multiprocessors, the uniform memory architectures, and that is just a small slice of the possible design space. Still, this is from a commercial standpoint, this clearly dominates this scope of multiprocessors. But we will get back to this picture later once we understand more of what a multiprocessor is, and then I think you will be able to appreciate the different flavors of multiprocessors. This is not a course about programming, but we still need to understand what this unit of parallelism is that we will discuss in this course. So we will talk about thread-level parallelism. And typically when you have thread-level parallelism, you have managed to create some number of parallel either processes or threads. So if you like to create some number of parallel processes, you use in Unix or Linux, you use fork or the and sign at command level. So if you ls and ls, you will actually start two ls in parallel in that world. If for processes, one of their properties is that the different units of parallel execution called processes, they will each have their quite a lot of their own state. For example, each process will have their own mapping from virtual to physical addresses. In contrary, you can have threads, which is a little more lightweight unit of parallel computation. Threads, you can, for example, create many parallel threads with the command thread create in the standard POSIX. The difference here between processes and threads is that threads, these parallel threads you create that way, they share much more state. For example, they typically share the virtual to physical mapping of addresses between all the threads. You can also have, of course, have threads inside processes. You can have parallel threads, and you can have parallel processes, and each of the parallel processes can have parallel threads inside them. But you cannot have parallel processes inside parallel threads. There are lots of other ways to create parallel units of computation, and we'll discuss that a little bit more when we prepare for the labs. So you have OpenMP, OpenACC, OpenCL, there's a language called Silk, and so on. That makes the parallel programming a whole lot easier than the POSIX standard. So what's a common property for all these languages and all these different parallel executions is that each unit of parallelism, be it a process or be it a thread, has its own program counter. So each parallel thread will have a special register, the program counter, that points to the next instructions to execute. So they can possibly execute different kind of parallel programs. Sometimes all the parallel threads execute exactly the same parallel programs, but the threads can be execute different instructions at the same time in that parallel execution. So we'll talk a little more about how to create parallel units of computation during the lab lectures. Now I assume that there is a way to create some parallel execution, and we will see what kind of programming model that we may explore in such parallel programming style. So we're going to talk about something called coherent shared memory or coherent memory. So the programming model of coherent memory is that you have some parallel execution. So in this example, we have some number of parallel threads, and as I said before, each thread has its own program counter pointing to the next instruction to be executed. And all these instructions executed in parallel in these threads read and write from some kind of shared memory. So this is the programming model. But as we all know, if this is a DRAM, it's slow and it has very low bandwidth, data bandwidth. So in order for this to be a high-performing system, we have to introduce some kind of caching. So we will put a layer of caches or one or many layers of caches between the threads of computation. So this would sort of be like what's going on inside the CPU. Look at this like a bunch of CPUs, each reading and writing from their private caches. Could possibly be some shared caches as well here. And then only if you miss in all those caches will you have to go to the shared memory. So this means that introducing the caches gives the illusion of a shared memory with a shorter memory latency, but also with a higher memory bandwidth, because these threads can read and write from their caches. They think they read and write from the shared memory, but in real life, we have to sped that up. We're going to look at one generic shared memory architecture throughout many slides now, so just want to make sure that you all understand what this picture means. We have some number of threads, so look at this as parallel threads of computation, or look at them as CPUs or cores executing at the same time. We have shared memory. In the shared memory, we have some number of data objects, and these objects, as we know, are going to be organized as cache lines because we're going to drag these cache lines into the caches. We have the blue boxes that symbolizes some cache hierarchy. So even though we just have one level of caching here, it's sort of a generalization of many levels of caches that may exist in the system with L2 caches, data caches, and instruction caches, as in this example. We're going to look at what instructions these threads or CPUs are executed, and we're going to look at some specific interleaving of this execution because these threads execute things in parallel, but we're going to try to define exactly in which order these instructions are executed. So we assume that time is progressing as we move downwards here. And finally, we're going to look at the cache lines that reside in the caches. So they are just colored blobs or rectangles here in these blue caches. First, we're going to look at a phenomenon known as automatic data replication. Assume that the thread to the left executes some read accesses to the variable A. That means that the cache line containing A will be installed in its cache, and now we can read and write many times from its local cache with high bandwidth and low latency. And if the other threads also access A, they will also get a copy of A installed in their caches, and as you see, the thread to the right also accesses B, so gets a copy installed of B. So we automatically replicate data in many caches if many of the threads are interested in the same piece of data, and that improves performance. But it also creates problems. So let's say that one of these threads with a shared copy of A wants to change the value of A. So what should happen now in order for us to implement a coherent shared memory is that we have to make sure that it's a coherent view of the value of A. We cannot allow the thread in the middle to have one opinion about what the value of A should be, and the other threads have a different opinion, because remember, the programming model here was a programming model that didn't have any caches inside them. The programming model assumes that all the threads read and write from the shared memory. So we have to implement hardware that keeps this coherence, and a popular way to do this is to implement a write-invalidate cache coherence scheme. So this is something that the hardware will take care of. And what the write-invalidate will do is that when it detects that one thread wants to make an update to a cache line which is shared, or which it detects that this may be a shared cache line, then hardware has to step in and make sure that coherence is kept. And in this example, write-invalidate means you invalidate all the other shared copies in the system. And after they have been invalidated, then you are allowed to change the value of A. So now we have the new value of A, but only resides in one place. So that's the problem with writes. But there are problems with reads as well. So let's say the thread to the left wants to read the value of A. Now we have to make sure that it will not be able to access the old and boring value of A that still resides in memory, and have to make sure that it will get the new and exciting value of A that was just recently created by the middle thread. So we have to make sure that the hardware implements something we call cache-to-cache transfer to make sure that the new value is that the cache in the middle will answer this read request and not the shared memory way up there. A third thing that we also have to take care of is how to replace dirty data. So the data cached in the middle cache, and also now the data in the left cache, have a new and exciting value which differs from that in memory. So when the sad point in time comes when it's time to replace this cache line from the cache, because we need to put some new and fun stuff in that cache, it's going to be kicked out due to some replacement strategy, LRU replacement, random replacement, I don't know what, but it's been chosen now to be thrown out of the cache. And what has to happen now is that since it's dirty, we have to make sure that upon replacement, we will have to update the old and boring copy in memory, so it now instead contains the new and exciting copy of that cache line. In the right cache, we have another data object, the data object cache line containing B, and upon replacement in of that cache line, we do not have to do a write back. We can just simply toss that cache line over our shoulder because it has not been modified. has the same value as the value in the cache. So that's how we handle the writes, the reads, and the write-backs in a cache coherence system. So summing up coherence, coherence defines a property about a specific piece of data. And a sloppy way to define this is to say that there can be many copies of a datum, but only one value. And when you say this, you also assume, of course, only one value at any given point in time. And this is a very common definition, or a paraphrase of this is often used in definition, including a book that Mark Hill recently published. And it is a good intuition. It gives you good intuition what coherence is, but it's unfortunately a too strong definition, and Mark agrees with me on that one. So when you implement coherence, you may actually implement a system that violates the first definition here. They can actually be different values of the same piece of data, alive and readable in the machine at the same time. We will just in a few lectures see an example of that. I think a better definition of coherence is to say that there is a single global order of value changes to each data. So let's assume here that we have one thread that observes some data value of A going from 1 to 2 to 3 to 4 to 5 to 6 to 7. One way to sort of observe that would be for that thread to itself write these values, write 1 and then 2 and then 3 and then 4 and 5 and 6 and 7. So then it knows that the value 1 occurred before the value 2 and so on. So it has observed an order between those data values. Then if a different thread running at the same time observes some order, says, first I saw 1, then I saw 4, and then I saw 7 as the value of this value of A, that's also okay, because it doesn't violate the other order. There is still a single global order of value changes, where the thread to the left may have seen more of those values than the thread to the right, but they are at least in agreement about that. The sum of the observation made by thread 2 and thread 1 would create that global value order. However, another thread, 3, that have seen that the value of A went from 1 and then to 8 and then to 7, if that is a possible observation in a implemented shared memory system, that would not be a coherent system. Another definition that people are trying out is to say that one property of coherence is that after a computer stops, if all the execution in a computer stops, within a finite time, all copies should have the same value. So at a given point in time, they don't have to have the same value. But if you stop all the execution after a while, it should settle down, the memory system should settle down, and there should only be one value left. So unfortunately, I cannot give you a one stringent good definition. I give you the intuition, but at the same time, I can tell you that that definition at the top there is one that we will violate in this course in just a few slides. Still, from a programmer's perspective, the first definition is quite okay. Actually, if you write a program based on that intuition, you will write a correct program. So where do coherence matters? Well, we have a picture of a multi-core here again, and where we have, in this example, 8 cores. Each core has some number of private caches, L1 and L2, and then there is some kind of interconnect called the crossbar that connects all these second-level caches to each other and also connects them to the third-level cache. So where coherence matters in this picture would be, for example, between all the L2 caches, because here you have lots and lots of private caches or different caches sitting at the same level in the cache hierarchy. So we have to apply cache coherence here. Just looking at this picture, it's not obvious that you need to implement coherence in the third level cache, because as you can see on this picture, the third level cache is just one single cache. So all these threads running at the bottom of this screen, they will all share the value. So there will only be one value of A stored in the shared cache. Therefore, you would not need to implement coherence. However, as we also discussed briefly in this course, also on a multi-core chip, there are often some kind of links that allow you to connect several of these chips together. So if you connect several chips together and you want them to implement a coherent shared memory view between all those chips, then you actually will have to implement coherence in the third level cache as well, because now the third level cache will also have there will be lots of replicated third level caches at the same level in that new cache hierarchy. So also on the quick path interconnect by Intel, for example, we have to implement cache coherence somehow. So in summary, coherent shared memory programming models require some kind of coherence, and we saw some definitions of what coherence may be. There can be multiple copies of a piece of data, but only one value. Sloppy, but okay from a programmer. There are also non-coherent shared memory models. One example of that is what you can find in single-sided MPI implementations or some new programming models called PIGAs. We will not cover any of those programming models in this course. So the coherent shared memory programming model, that is a model where all threads can read and write to share data or shared memory. That's a fairly simple model, at least so far. And we require there to be a coherent view for the value of a specific datum. And finally, we can note that the coherence in a shared memory system is typically not kept at the byte level or kept at the word level, but instead we keep the coherence with a cache line granularity. So when the boxes, and that's what I also said when we talked about the cache coherence example, the unit of data that's installed in the caches and the unit of data that is being invalidated and written back with writebacks, that unit is the cache line, exactly the same size cache line as we've seen in previous lectures.